The conversion gain of 30 dB is after the baseband.
Yeah. Yeah. Yeah, so basically that translates to baseband amplifier gain of whatever gain you get from LNA and whatever degradation you have from the mixer times could be equal to 30.
The amplifier itself will be just a different.
Up to you to design, doesn't matter. So can be pseudo differential, fully differential, two single endeds, totally up to you. Yeah, the part that I didn't mention, maybe also I'll put an addendum, is even though there is no specification on image rejection, but you should note down what is the strength of the image. Okay, so it's about time we start on something else. We have been doing receivers for quite some time. So what else in RF other than receivers, transmitters? So we have only 2 classes, so obviously cannot go into too much of the depth into transmitters, but 2 classes will be enough to 2.5, let's say the half of last class will be enough to give you an idea about what are the trade-offs in a transmitter. Given that we have spent quite a lot of time in using receivers, I think it should not be too difficult for you to understand the trade-offs, and let's see where we go from there. So let's start off with the receiver topology and then show how a transmitter is similar or dissimilar from a receiver. You have a transmitter where you maybe have a SAW filter, then you have an LNA, then let's say you have image reject. You have image rejection topology, then you have mixer. Then you might choose to have a band pass filter or a low pass filter. Why do I say band pass filter or a low pass filter? Any comments on whether, I mean, to understand why do I say band pass filter also? Right. So here, if you have image rejection, which means this is a super heterodyne receiver, right? This is not direct down conversion. This is super heterodyne, which means the input here can be at omega LO. By the way, this is always omega LO. This is omega LO plus minus omega IF, where one of the either plus is the frequency of choice and the negative is the image, or the other way. So which means that here you are going, after down conversion, you are going to have signals at omega IF, not around DC. Now if you choose omega IF to be like 100 megahertz, if IF to be 100 megahertz or 200 megahertz or 500 megahertz, then probably it's better to make a band pass filter than a low pass filter, significantly at a higher frequency. If it's like 10 megahertz or something, then low pass filter will also suffice. The only only downside to it is that your baseband bandwidth is only like, in most cases, probably a couple of megahertz, 10 megahertz or so. So if that is the case, and you have a significant part of the baseband spectra where you do not have any information, then it's better to use the baseband filter. Band pass filter. Otherwise, low pass is also fine. So I leave the choice up to you for the assignment. If you want to use BPF, you use BPF. If you want to use LPF, you use LPF. And then this part we haven't done. If omega IF is significantly high, right? When I say high, I mean hundreds of megahertz, then you kind of have another set of down conversion and a low pass filter. Right? So for your project, this will not be required, but yeah, I mean, this is something that is also done. And then what you do, you put a ADC. And after ADC, then you either, depending upon what is your application, you either cast the bit on a screen, or you store it in a memory, or blast it through a microphone, whatever. I mean, but that part of storing it in the memory is a part of the overall receiver. But the other two examples that I gave involves a transmitter, because you are again taking whatever has been stored and transmitting it through an actuator. Right? So the transmitter is something that we are going to start looking at. Okay, right? So again, a very brief architecture of a transmitter. So you basically do the reverse. You have a DAC. You convert the digital. This is digital. You convert the digital bits into analog, right? After a DAC, for those of you who have taken data conversion courses, you must be familiar with it. Again, this will be a square wave kind of waveform. Even if you have not taken data conversion courses, it's okay. What I essentially mean that what is a DAC? DAC is nothing but you see a set of bits here, and you associate a voltage level or a current level with each bit, right? Which means there is a discrete levels, and which essentially means that the output of the DAC is not necessarily very smooth. You'll have square wave, or depending on what type of DAC you have, you are going to have different types of waveforms scaled with respect to each other, which essentially is an analog form of the digital bits. Now, then obviously, if you have the scaled periodically sample bits, which essentially means that you are going to have multiple harmonics or sidebands, just like you had, you would have sideband after you sample, right? When you have analog signal and you sample it, you are going to have aliasing, right? You are going to have, or I shouldn't say aliasing. When you take an analog waveform and sample it, you are going to have tones, right? Similarly, when you take digital bits and you associate an analog value of that, it is equivalent to sampling an analog signal, right, at this node, which means you are going to have tones. But the information that you are going to send out should not have tones, right? Because you are only sending out, let's say, your IF or your bits or your frequency of choice is maybe audio or a video, which may be a kilohertz or few megahertz. If you are sending out 10 megahertz signal, you don't want tones at 20, 30, 40, 50 also, because then will be sending out those tones also. So which essentially means that you need another sort of filtering, right? So you put another filter. Now, again, depending upon whether you want it to be, depending upon where the tones are, you choose what type of filter you have, but mostly if you have a band pass filter, this should be fine, right? So, and then what is the frequency at? Here you will have baseband plus minus harmonics of baseband, right? Here you are going to have only omega baseband. Now, omega baseband can maybe around DC, maybe around some non-zero frequency. So you decide whether you want to have a bandpass filter or a low-pass filter based on that. But in most cases, it is not exactly around DC, so you end up choosing a bandpass filter. So now you have an analog. Think of a sinusoidal signal here. So all you have to do is put an amplifier, which we call it as a power amplifier, and send it out. And ideally, we send it out through the same antenna. So you have another SAW filter connected here, something like this, right?
So what's the up conversion?
Oh, I missed the up conversion. Sorry. Thank you. Running ahead of myself. So yeah, so after band pass filter, obviously you need to up convert, otherwise you are never going to send it through an antenna. So maybe at omega LO TX, like say omega LO RX, and then you again you are going to have set of images, right? Because you are again multiplying, so you kind of have a band pass filter. Then you have a PA. Now, depending upon whether omega LO TX and omega LO RX are same or different, you have different types of topologies. If they are different, then you can simply connect to the same antenna through the through two sets of SAW filters. If they are same, then you need a switch. Then you are essentially saying that I am not receiving and sending at the same time, right? I am either receiving or sending. So based on that, you need to have a switch directly connected to the antenna, right? To ensure that it either you either configure your transceiver in the receiver mode or in the transmitter mode, right? Okay, fine. So what we have been focusing on till now is essentially this. In next couple of classes, we are going to focus on the transmitter side. Okay. So as you can see that on a block diagrammatic level, your transmitter is essentially looks like the flipped version of a receiver. Right? So whatever you do in a receiver, you undo in a transmitter. Right? So what I will do is I will concentrate from, I mean, the mixer topologies are something similar to that of a receiver. There is a slight variation, but we'll talk about the variation later. But as of now, assume that the mixer is exactly same as the mixer receiver, with an important distinction that the input of the mixer is now at baseband. Right? In a receiver, the input of the mixer was at RF. Here, the input of the mixer is at baseband, right? So that way, that is the only difference. I mean, if I have to draw the mixer, so again, you can think of it like the same guy. Let me draw only two parts. I don't want to draw four parts. And this is at omega LO, right? And then you have F, and then so this mixer topology is almost identical to whatever you had in the receiver. But the key thing is that the output filter requirement might change based on whatever you are trying to transmit or filter out. Okay. Okay. So before going into PA, right? So or PA topologies, let me ask you one simple question. Hopefully that will answer some of the fundamental questions associated with PA design. One is, let's say, I mean, ultimately, we all know there is one amplifier in town. It's a common source amplifier, right? You have to use it in that way, in some fashion. If I say that, let's say I have a common source amplifier, you can put any sort of load, resistive load, inductive load, doesn't matter, some ZL. And I am putting an input here, right? Which has the resistance associated with it. And I'm interested in the output across the amplifier, across the drain to source. And I'm interested in power amplification. I'm not interested in voltage amplification or current amplification. Okay. Just like in 610 or 613, you start off the course saying that we want to make a power amplifier, and then you see what are the constraints and Y parameters to get power amplifier and so on. So in this case, if I say that, can I use this common source amplifier to get power amplification at any frequency? When I say any frequency, I mean it can go to like hundreds of gigahertz, terahertz, hundreds of terahertz, millions of terahertz. Is it possible? Obviously, it's not possible. Why is it not possible? Gate capacitance. Right? But this capacitance I can tune out, right? In a narrowband sense, I can tune out this capacitance. So now, is it possible? There will be a transit frequency constraint. Yes, right. So there is a constraint, but yeah, it's related to transit frequency. So then what? What does transit frequency, from where does the transit frequency come, that constraint? We need to have some current gain. That is correct. I agree. But the thing of transit frequency comes because you have a capacitance and there is a voltage drop, and corresponding GM/VGS also drops. Kind of, right? But if I tune out the capacitance, then that should not be an issue, right? Then let's say it's a unilateral device, no CGD cable. I give a hint. This topology, the way I have drawn, it can give you gain at any frequency, power gain at any frequency of interest. There is something wrong in the way I have drawn it. I have not included a very vital thing, which we have neglected mostly. But when you talk about very high frequency stuff, you cannot neglect that. Or power gain, you cannot neglect that. Let me put it that way. Power gain at high frequency. Pardon? There is the current path, voltage path, yes. So okay, I mean it takes because you have a capacitance. Yeah. Right. So there is essentially is the problem with the model. If the device does not draw any power at the input, I can get a power at the output, which means I'll always get infinite power gain, right? Just think of a common source amplifier the way we treat it, right? It's a capacitive input resistance. So, right? So it never consumes any power at the input side. At the output, I get power, which means I have infinite power gain, always. That is not true. In truest of sense, at very low frequency, it's maybe okay. At high frequencies also, if the way we model, it's a capacitive input. Capacitor does not draw any power. So I should get infinite power. What I'm saying, something is wrong with that model. What is wrong with that model? Yeah, I agree. I mean, that is you're talking about the DC power getting converted to AC, right? So let's say small signal. Everything is small signal power gain. Didn't understand. Ah, ah.
The default, the AC coupling current short.
Which AC coupling?
The incoming signal source.
Yeah, small signal that is shorted. AC coupled signal shorted. Don't have to bother about bias. It's nothing to do with bias. Gate consumes current. That's the capacitance. Gate definitely consumes current. At high frequency, it will good. No, it will consume. Thus, the current will go into the capacitor. You are not drawing it from the source. It will have a current, right? For example, if you have this at steady state, at resonance at steady state, does a capacitor have a current? It has, right? Yeah, so it has. So that loss has to be compensated. Who is going to compensate for the loss? The source. If there is an inductor resistance, right, is a loss in the network, there will be a loss, and that loss will be compensated by the source, right? That's how you reach steady state. Here, I did not mention this, but let's say I have a resistance here. So there will be a loss. So something of this has something like this is a culprit. So gate resistance, for example, right? We have kind of summarily neglected gate resistance in most analysis, but for some noise analysis somewhere, right? But in PA, that becomes an issue. Even, I mean, a couple of ohms of resistance can be a big issue when you're talking about very high power. We are going to see what are the impacts shortly, but what I am trying to focus here is you'll have a gate resistance. And you are going to have a capacitance. So this is your input of the device. This is CGS, right? So what I would like to do is find out what is the power delivered at the output for this model. Okay. So what is, so let's say P. So this guy delivers P in, right? So where will P in get dissipated? Whatever the P in that you are extracting from the source? From RG, that is the only place it can get dissipated, right? So essentially your P in is equal to half I in squared times RG, right? And again, I am interested in the final output current, which means I'm interested in the VGS, right? So I know that I in is essentially J omega CGS times VGS. So in terms of P in, this becomes, so if I plug this in here, so P in becomes half of omega square CGS square VGS square RG. Similarly, your output current I out is GMVGS, and your P out is half I squared R, which means half of GM squared VGS squared times. Let's say I'm only interested in R out, so that is the intrinsic gain of that comes with the MOSFET, right? You cannot do better than that. So I say this is equal to times R out, which is essentially equal to, I plug this in, What do I get? With a mistake anywhere. Fine, no issues. Of GM squared. So your P out over P in. Yes, this dm by cgs becomes omega t. So you get omega t by omega whole square times r out over rg. Now, in the literature, if you look at this result, you are going to see there is an additional term of 1 over 4. That comes, there is an additional factor that comes because in many cases, this calculation is done under matched condition at the input. Right. So here I have talked, I'm taking the amount of power you are extracting into the input, not with respect to the final input source. So there will be a difference with respect to whatever you see in the literature, but nevertheless, I mean, that factor is not of importance. The importance here is you are going to get a power gain, which is actually and this power gain goes to unity at, this is called omega max. That is a maximum power, maximum frequency where you can get a power gain, which is related to omega t. Okay. So you see that it is depending upon, I mean, this obviously is much more than omega t, because typically your RG will be of the order of couple of ohms. And R out can be, I mean, even if a very crappy transistor you use, R out can be like 100 ohm or something like that, right? Or even 50 ohm, depending upon what GM you are sizing for, obviously. So what I'm trying to say is that you can get omega max, which is more than omega t, but it will never be infinity, right? So as it turns out, in power amplifier, there is a trade-off. There is a very interesting trade-off between this omega max and the amount of power you can deliver also. So I have not talked about it till now, but you should be able to get an idea from whatever I'm going to say next. So if you have a common source amplifier, let's say I have this, maybe a current source bias or something. The bias is not important. I'm only focusing on the MOSFET. So if I have to get a lot of power at the output, which means that this guy will swing. When this guy swings, naturally, as far as the breakdown voltage of the MOSFET is concerned, what can you comment on? It is becoming closer and closer to breakdown or away from, if the swing is more? If the swing is more, is it the MOS is getting, it is pushed towards, being pushed towards breakdown, right? So there is a limit to how much swing you can have at the output of a MOSFET before it breaks down. Now, depending upon technology, that output limit can vary. For CMOS, it will be something. For gallium nitride, it will be something, and so on. But there will be an output. There will be an output limit. Yes. Okay. Question is, why does it break down? So typically, I mean, goes back to the things that we learn in, I mean, when we talk about capacitors at the beginning of maybe class 12 or something. So you have this dielectric, right? So you have this electric field. So every dielectric has a maximum electric field before which it pulls out the electrons away from the atoms, right? So you have a breakdown field based on associated with each dielectric before it punches through. It's no longer an insulator; it punches through, right? So dielectrics have, again, at molecular level, you have these atoms which have this outer circular orbits. Ideally, they are well quenched. I don't even remember the chemistry right now. But I mean, essentially you have these s orbitals, p orbitals, so on, right? And supposed to be very stable, but when you but the electrons and the protons are not co-located, right? So there is an electron cloud and there is a proton cloud, not a proton cloud. There's a place where the positive charges reside. So if you give an electric field, you are kind of the electron cloud you can skew out with respect to the proton cloud, and that creates the plus and the localized plus and minus dipole, right? Each electric field, each dielectric, each atom in the dielectric creates a dipole, and that's what gives you the dielectric constant to some extent, right? So dielectric, another way of defining dielectric constant is how much it is able to nullify the electric field to some extent, right? But anyhow, that's not going into that that discussion. Yeah. So basically this. So if we know this, what we know is you have this capacitor here, right? Similarly, you have a capacitor from here to body. So this is CGD. You have CDB, right? So which essentially means that the dielectric associated between those two can start to break. Now, can you comment on which one will break first, CGD or CDB? Probably not a fair question, but in your experience, or what do you think based on the thickness of the dielectric? Let's say you have a thick, you have two capacitors in which one dielectric is thicker than the other. Which one will have a more? Thinner will be having more breakdown voltage or less breakdown voltage? Less breakdown voltage, right? So as it turns out, the CGD capacitance has this dielectric thickness of TOX, right? It's basically the overlap capacitance between the gate and the drain. But the CDB capacitance is what type of capacitance? Pardon? It's a junction capacitance. It's a reverse bias PN junction capacitance. So in a reverse bias shallowly doped reverse bias PN junction capacitance versus this TOX, which one do you think is thinner? TOX is obviously thinner, right? So which one tends to break first? CGD typically tends to break first, right? So what is the solution to go to higher breakdown? I'm not talking about topology change. I mean, whatever you can do in a topology, you can do in any other topology also, any other process also. Different transistor with a thicker oxide, right? So typically, even the technology that you are using, all technologies typically tend to have two flavors of transistors at least, one with a thinner oxide, one with a thicker oxide. The thinner oxide transistors will typically will be labeled as a lower voltage supply, right? Some NMOS 1 volt, something like that. And a thicker one will be labeled as with a higher voltage, some NMOS 2 voltage or 2.5 volt or something like that. So that does not mean that you get the same performance with a higher voltage. It means that has a higher breakdown voltage. Now, as it turns out, there is a trade-off with that also, because when you have a thicker oxide, the gate control of the channel reduces, right? If I take you back to the basic MOSFET courses, so you want inversion in the channel, which means you need whatever electric field or whatever voltage you apply at the gate, that should be able to create the inversion layer, and not only create the inversion layer, for every unit change in the voltage there, it should be able to sufficiently influence the charge in the channel, right? So if you make a thicker and thicker electric field, as it turns out, without getting too much into details of the devices, as it turns out, the gate control reduces of the channel. That should make sense at a very zeroth order level, right? So one capacitor plate is far away from the other. So obviously the amount of charge that you can influence on the other plate will be lesser. So which means that in order to restore back that influence, you need to have a bigger channel, right? So which essentially means a larger L. So thicker oxide devices typically tend to have larger L. So what is the trade-off with a larger L in terms of omega T? Omega T reduces because omega is directly proportional, inversely proportional to L squared. I mean, if I go back to the square model, which means that if you want larger power, you have to use thicker voltage devices, which means omega T is going to reduce. What can you talk about the omega max? Is going to reduce, right? So as it turns out, there is a very hand wavy, but for MOSFET, any any CMOS device, given that your breakdown, the CMOS device made with silicon dioxide dielectric, this F max is around 200 gigahertz. If basically the F max where you can get power gain given certain amount of breakdown voltage. That there is a trade-off. Okay. So that is why it's very difficult to push CMOS voltage. I mean, that is all again a very hand-wavy approximation, but for the purpose of this course, only thing you should appreciate is that it's not like I can go to any frequency that I want and get a power gain. Okay. Fine. Any questions so far? Yes. Can you repeat? I cannot hear. Yes, right, exactly. So when you use a 45 nanometer or 65 nanometer technology, the minimum channel length that is referred to is whether 45 nanometer or 60 nanometer or whatever. That refers to the maximum. That refers to the fastest transistor available in that technology. And typically, the fastest transistors are supposed to have the minimum channel length, right? Because ultimately, one of the metrics of speed is how fast you can push electrons from drain to source. If the channel length is bigger, you are going to make it slower. So the fastest transistors tend to have minimum channel length, but they also tend to have lowest breakdown voltage. So that's why when you use PA, if you are not very close to this omega max, you tend to use thicker voltage devices, which are not as fast as whatever you find here while designing the LNA, for example. Okay. Fine. So that's one design constraint, one design challenge, or rather one design choice that we should make. Now let's go into PA architectures. So given that we know that we have to use high voltage devices. So this is something that we had talked about it probably one of the very earlier classes about efficiencies of amplifiers. So quickly, so let's say I bias a common source amplifier. Now I'm coming back to neglecting RG again, because I'm assuming that we are operating at much lower frequency, right? Yes. Yeah, it's basically L, right? W over L you want to maximize. But anyhow, go ahead. Yeah. Cox essentially. Cox is epsilon ox by Tox. Right? So Tox is thicker. Right? Yeah. So you basically if you can think of it this way, the IDS, the unit change for every delta V VGS basically boils down to GM. So if for every delta V change in VGS, how much delta on your current you are getting for the same W by L, it is basically then proportional to Cox, right? Again, I mean you should be slightly careful in taking that argument too far, because all of this assumes that the electric field in your capacitors are vertical. There are no fringe field. Nothing is going like this. This is correct. So generally, if you have a very tightly coupled metal plates, this is true, right? You kind of do like this and this. But if these metal plates are far apart, then it's quite likely that you are going to have these big fringe fields and some like this. So So which essentially means that your capacitance models are more accurate here and less accurate here because you have things going bulging out, maybe going somewhere else also. Right? And after some time, it is not even going to behave like you double the area of the capacitance. Your double the area, the capacitance need not necessarily double also, because your fields are going away. True, but to some extent that is still in your control. You can increase W. Again, there is a trade-off, but yeah, but you are thinking in the right direction. That's another problem. Yes, yes, we are making the GM bigger. So essentially, we are going back technology nodes. You can think of, right? So 20 years back, people used to use 1 micron technology. 30 years back, maybe. Now you use like research papers are coming out in like sub 10 nanometer technologies, or maybe 28 nanometer is one of the common nodes for analog. So you can see in 30 years, we have gone from 1 micron to let's say 20 nanometer. But for those are for high frequency devices. If you have to use high power devices, then you cannot go to 28 nanometer. Right? So essentially, even a 28 nanometer node or a 45 nanometer node gives you a thick oxide devices, which is equivalent to going back a few technologies. You're going back to 180 nanometer maybe, or 250 nanometer, because they have higher threshold, higher voltage swings available. Again, this is not a generic thing. This is again based on how much swing you want. Let's say you want a swing of minus 10 dBm, fine, you can use the low voltage devices. But if you want like 20 dBm, then you have a problem. Okay, so now let's see this, revisit this class A, I mean, this type of amplifier topologies. So this is, let's say, biased. Now, since you have already done one example of this earlier. So by the way, if I ask you to do the first assignment now, would you do it better? I would hope so, at least. Fine. So now I would like to find out what is how much power, what is the efficiency of this network, right? So to find out the efficiency, what I need to do, I need to find out input power, I need to find out maximum output power, right? So let's find out the output power, then we'll go to the input power, right? So what will be the output power? So the current IRL, so your P out is half IRL square times RL. So what is the maximum IRL that you can get? It will be IDC, right? So your P out max is half IDC square times RL. And if you have, if you are satisfying this criteria, what will be the voltage swing at this node? What will be VDS? How will it look like? So what I'm saying is your IRL, let's say, lowers like this. So what will VDS look like? So in order to find out what the VDS look like, you need to tell me what does IDS look like, right? What will IDS look like? Right? Yeah. So basically IDS plus IRL should be equal to IDC. Right? When one is maximum, other is minimum, so it should be something like this. IDS cannot go negative, by the way, so it has to go from. So that the sum always remains IDC, right? Fine. So if that is the case, what is the so why am I doing this? I need to find out the power delivered, or not power delivered, right? Power dissipated. Power dissipated is nothing but this IDC times the average VDS, right? So this is IDC times VDS average. So in order to find out average VDS, I need to know the profile at VDS, voltage profile at VDS. I know the voltage profile of VDS is sinusoidal. So basically, I need to find out the average of the sinusoid. So what will be the average? Which is equal to, under this condition. So this goes to 0, right? So when IDS is maximum, right? When IDS is maximum, what will be VDS? Okay, tell me this thing. When IDS is minimum, when IDS is 0, what will be VDS? Which will be, yeah, which is equal to value. Yeah, so in terms of you know the voltage, you know the swing across the resistor, right? What is the swing across the resistor? IDC times RL is the maximum swing, right? So essentially your, so this guy, oh, this should not, this is current, right? Your voltage will be, I have to plot in a different plot. So tell me, when will be the voltage be maximum? No, what I mean is when IDS is maximum, voltage is maximum, or the other way around? It's the other way around, right? So okay, fine. So now essentially means that so this I know is 0, and this will be IDC times RL. So that is the maximum swing that you can anyhow get, right? Okay. No, this is the voltage across the MOSFET. Voltage across the resistor goes from plus IDC RL to negative IDC RL. Voltage across the MOSFET is basically one capacitor voltage above, right? But I don't know what is the capacitor voltage above, as is, right? From the constant that I've told you. But one constant I know is that the MOSFET voltage cannot go beyond, VDS cannot go negative. I'm assuming V overdrive to be 0 and all, right? So your MOSFET voltage cannot go negative, which means the minima is 0. Maxima I know, because peak to peak is anyhow how much? 2 IDCRL, right? So this should be 2 IDCRL. Right? So then I know the minima and the maxima of the sinusoid. Then the average I know. Average is then IDCRL, right? So your then VDS average is IDCRL, which means that your efficiency is half IDC squared RL by IDC squared RL, which is 50%. Right? Does that make sense? Okay. So 50% is, I would admit, it's a very good efficiency, right? I mean, if you look back to whatever you got when you designed, it's much better than whatever you, it's the maximum theoretical limit if you have an ideal current source. Okay. So now you do not have an ideal current source, but in RF, you have something which can mimic an ideal current source. What is that? An inductor, right? So which means that I can probably have an inductor here. Okay, so this can in principle give you 50% efficiency, but there is an issue. Not with respect to efficiency, but with respect to the maximum power you can deliver. Why? Because let's say I target a power delivery of 20 dBm, right? So let's say target the out target is 20 dBm, which is in a linear term is equal to 100 milliwatt, right? Your RL is typically an antenna which is 50 ohm, correct? So how much swing you are expecting at the outside across RL? Half the RL squared times 1/50 is 0.1. Okay. So VRL squared is 10, which means VRL is approximately 3 volt. 3 points, just taken 3 volt, right? So which essentially means that peak to peak, V peak to peak or VRL peak to peak, six volt, which means the swing here is 6 volt. That's the problem. You're never going to get 6 volt swing with even the 2.5 volt devices or 2 volt devices. You're never going to get 6 volt peak to peak swing, right? So can you suggest a solution then, given everything that we have discussed in this course till now? Right. So the key is, I mean, what do I not want to compromise? I do not want to compromise the voltage swing across RL, but I want to reduce the voltage swing across the device, right? So basically then only way I can do is probably use a transformer which transforms this RL to a lower, the device sees a lower impedance, but the 50 ohm exists somewhere else, right? We need an impedance transformer. So I put a matching network then. I am showing it as a transformer, but you know what type of matching networks you can use. So the impedance looking here is RL over N squared. And so if our impedance looking here is RL over N squared, what will be if all the other constraints like 3 volt swing across RL and everything is met, what will be the swing here? Now V peak to peak. 6 by N. So why N squared? Right, both of them go, right? So that's why, right? Okay, fine. So if I have to bring it down to 2 volt, peak to peak 2 volt, then N should be equal to 3, right? So you basically then design your matching network so that the trans ratio is that and you are good. But there is an issue. So the issue is this. So now let's say N is 3. I'll round it off to say that N squared is 10. Because that's what it should be, right? Ultimately, you are bringing it down. There's two approximations canceling each other. So if that is the case, then effectively this guy sees 5 ohm impedance, right? And there is a matching network. Ultimately, things are going to get dumped properly. Understood. There are two issues here. One is matching networks have finite Q, right? Another issue is this nicely drawn wires that I am having. We are assuming they have zero resistance, but they do not have zero resistance. It is very easy to get couple of ohms resistance with normal routing, right? So if your matching network, let's say, has let's assume omega Q of typically on chip, let's say Q, if I'm being very generous, let's say Q of 20, right? At omega equal to, let's say, 1 gigahertz. So what will be R for for the matching network? Effectively, let's say it's inductive R. Let's say omega L by R equal to 20. What will be R? The L by R is equal to 20. R is like you need the value of omega L also, right? I have not given you value, but okay, fine. So based on experience, so you can get R to be approximately of the order of couple of ohms easily. So let's say 2 ohms of R and 2 ohms of R due to matching network and 2 ohms of R due to routing of this inductor and the device and all, right? Again, it's very easy to get 2 ohms. It's not like you can really get less than 2 ohms. So this guy gives you 2 ohms, this guy gives you 2 ohms. So now can you see the problem? With respect to efficiency? More than 25, like it's like 4 ohm here, 5 ohm there, right? Almost 50% power is lost in your device, routing itself, right? So your theoretical efficiency of 50% now goes down to 25 without doing much. Okay. So this essentially gives you another pointer that if you want to use a matching network, that is one of the reasons in PAS, the matching networks are often you see they are off chip. They are not on chip. One of the reasons is because off chip matching networks, which use like very good inductors and capacitors, they tend to have very good Q. Right? They do not have good Q at very high frequencies. When I say very high, I mean like if you go to 10 gigahertz or so, they are not going to have good Q. But moderately like 2 gig, 3 gig, 4 gig, fine. You can still use off-chip matching networks. They are going to give you fairly good Q and go ahead with it. Trade-off is you end up having a lot of board area, right? If you don't put anything on the chip, you have to put it on the board, right? If you go to our lab and see, like, so, I mean, how a compact board looks like if with respect to something which is not very compact, and debugging things on a board is another headache. And the board area directly affects the area of the technology it is going in. Chip anyway takes a very small area, right? So if you open up your cell phone, you will see that there are like dozens and dozens of chips inside, but they still take a very small area with respect to the board on which they are mounted, right? So if you want to reduce the size of your cell phone, you have to basically ensure that there are less and lesser components on the board, right? So that's another trade-off, right? Okay, how much time do I have? 10 minutes. Okay. Fine. Any other questions so far? Okay. So let's say you are not designing anything at 1 gig, you are designing something at very high frequency, like millimeter wave, 20, 30 gig, right? So then probably it's not a very good idea to put matching networks on the board, because you are not going to get very good Q with the onboard components, but you get kind of tend to get better Q with on-chip inductors. So then we decide to use this 1:n, 1:3 or 3.5, whatever, to get these power numbers. So then my question is there a way of reducing this loss that comes from matching network for a given turns ratio? Right. So right now your Q is essentially N. Right. So if you recall, we had one lecture in which we talked about how we can split the matching networks into multiple small matching networks and reduce the overall loss. Why? What is the root cause of loss in a matching network? If you have very large Q, you have large swing across the passives in the matching network. Right. So if you have loss in the passives, the loss associated with the large swing will also be higher. The way to reduce it is to have two matching networks. Product of Q1 and Q2 should be equal to whatever N you wanted. But right now, since these Q1 and Q2 are smaller, so you should be able to get a better matching network with low loss, right? That is why very high power devices, high power PS, do not have one single matching network. They are the distributed matching network. Okay, fine. So this is as far as class A. By the way, this I did not talk about topology name. This is a class A amplifier. I should say simply amplifier because this topology is not limited to PA. When I say class A amplifier, it essentially means that the MOSFET is always on, right? Regardless of whether I have in the positive half cycle or negative half cycle, the MOSFET is always conducting. Barely conducting at the negative half cycle, but still always conducting. So why is that distinction important? It's important because, so if I look at when I say you have 50% efficiency, which means there is a 50% power loss in the MOSFET. Correct? So where is the 50% power loss coming? It's basically the loss across the VDS of the MOSFET. Correct? So if I look at the current in the MOSFET, loss is basically VDS times IDS. Correct? So basically, in this plot, it's basically the multiplication of the red and the blue plot. Correct? So what if I find out a topology? So if I just plot it here for class A. Your IDS is maybe something like this. And your VDS is something like this. So the product of this, you get kind of as a loss, right? So the product of this would look like not drawn to scale, obviously, because this is so one way of then saying that if I let's say don't conduct okay, so the way to think about this is the following. So when IDS is high, right, or rather, what is the objective of making this amplifier? I would like to ensure that lot of current goes into the load, right, whereas lesser amount of current goes into your MOSFET. That's how you increase efficiency, right? But that statement is also not fully true. What I would ideally like to have a lot of current flowing into the load, but can I have a scenario in which when the MOSFET voltage is high, right, the product of VDS and IDS should be minimum. That's how I reduce the loss across the MOSFET. Correct. So one way to think about it is that when I am pushing current into the load, that is inevitable. I am going, that is desired. But when I'm drawing current out of the load, maybe that when I'm drawing current out of the load, that load current is now getting pushed into the MOSFET. Right? So that is not going to the load, but I am giving it an alternate path to go into the MOSFET. And that is also increasing the power dissipation in the MOSFET. Does that make sense? So what if I do not allow that path? If the when the voltage across the load increases, that is fine. All the current is going into the load. The MOSFET, most of the current is not going into the MOSFET. But when the current in the load is decreasing, that current is going into the MOSFET. And that is contributing to a lot of power loss. What if I do not find out a way of nullifying that part? I'll keep the good part. That is the current going into the load. That cycle I should keep. The other half cycle in which the current is being diverted to the MOSFET, I'll not keep. If that is the case, then intuitively we can assume that the efficiency should go up. Right? So I'm keeping the high power delivery cycle. I am lowering the low power delivery cycle. Right? Make sense? So what essentially it should look like is so in one cycle, this should go and give me a lot of power, right? A lot of voltage swing across RL. But at the negative half cycle, when I am taking current out from RL, that current should not go into the MOSFET. Okay. So what a trivial way to say the same thing is that I will not even have that half cycle. Right? So let's say your input is, this is input VGS. If I have if I have the operation such that I have only one half cycle, then here, I am delivering power. But here, no power delivered. And no power lost also. Right? Because ultimately, how are you going to implement this? We are going to implement this by ensuring that, and what is the easiest way of implementing this? Right. So essentially, the transistor should be switched on during one half cycle and switched off during the other half cycle. Right. So all I have to do is to ensure that this bias, whatever I have, is equal to VTH. And on top of that, if I apply input, then the effective V overdrive goes from 0 to maximum and then again 0. The negative half cycle doesn't come in. So which means here I get, if transistor is off, no power delivered, transistor is off, no power delivered, transistor is on, high power delivered. So this in principle should give me good efficiency. But obviously you see a problem, there is cutoff and all those things that happen, right? So we'll have a lot of distortion because of this. So the alternate thing to do is to say that if I use differential circuit, right? If you use another one, I should not say differential, I should say another replica of this, which operates on the negative half cycle. Then I can add those two currents up to get the full cycle. Correct? So how do I do that? So I have this one, this one. V in minus V in. So if I have a load connected here, and if I have a load connected here, so this load is going to see this cycle, this load is going to see this cycle, right? In principle, both of them are going to see the same because, I mean, with respect to, I should not sketch it like this. So this VO1 and VO2. VO1 should look like this, and VO2 should look like this. Correct? So ultimately, then you have to take the subtraction of VO1 and VO2 so that you get the full sinusoid. So how do we subtract? I do not want to use, obviously, this is at the output. I'm talking about very large power. I do not want to use the differential amplifiers and all. What is the easy way to subtract using passives? Using a transformer will help. Balun or a transformer. So I have this. So VO1, VO2. Trans ratio of 1. What will be the voltage here? Ideal transformer. So let's say I have a voltage here, V. What will be the voltage at the output? VO1 minus VO2, right? If I have a trans ratio of 1. So that I can do here, right? So all I have to do is put a transformer here. I can do even better because I already have the inductors, right? I don't need to put an explicit transformer. I can make the inductors, connect them in such a way that they become a transformer. For example, I can connect these two. So effectively, I'll redraw. So I will essentially say this. This is the VDD. And I have the another coil. Right? So this essentially becomes your class B amplifier. This is called a class. Okay. This is a class B amplifier where only one half cycle conducts from each of them and you combine the currents, right, to increase efficiency. I will show you the calculation. Have you done class B amplifier analysis before? No. So as it turns out, you get like theoretical maximum efficiency of 78%. That to some extent should make sense. It should actually at least have higher efficiency, right? Because of the reasons that I talked about leading up to this. Okay. Fine. We'll stop here. Thank you.